Hello. What we're going to do in this lecture is look at some consequences of the compactness theorem. So this was proven by Maltsev in the 1930s. Let's see what it says once again. So the compactness theorem. If I've got a set of sentences in a countable language, then for the set of sentences to be satisfiable, in other words, to have a model or a structure in which they can all be interpreted as true, it's necessary and sufficient that every finite subset of gamma has such a model. So I take any subset of gamma, gamma 0 finite, and gamma 0 has a model. Here. So this kind of possibly infinite set of sentences here, the problem is reduced to just looking at models of finite sets of sentences. And we saw last time how this was a simple corollary of the completeness theorem, because for a consistent set of sentences has a model by the completeness theorem. So if it's inconsistent, only finitely many of those sentences are needed to witness inconsistency. So then it comes down to a set is consistent if and only if every finite subset is consistent. And then after applying the completeness theorem, we get the compactness theorem here. So what we're going to do is continue looking at some of the consequences of this theorem. Now, you've seen one already in the first part of the course. So I'll recap that here, just so that we can see the kind of arguments that are used. So this is the example 5.5 on page 82. So it's an example of a non-standard model of arithmetic. So our usual standard model is just the natural numbers. And we take as two binary functions, plus and times. There's a successor function, add 1, and a constant 0 here. I'm omitting the superscripts, underline n here. So these are the symbols of the language, but they're interpreted in the usual way. So this is the standard model. Sometimes called the intended interpretation. The compactness theorem is going to yield a model in which all the truths of arithmetic hold, but it will not be isomorphic to this. It will have non-standard elements, which we would say sort of elements at infinity. Right? So we shall use the following. So in the notes, this is boldface n. I will put an underline here. So this will be a term of our language. So this is the term where I take the 0 constant and I put n many primes after it. So the interpretation of this in the standard model is just the number n. right? So I can think of this, or this, as a numeral. It's a way of naming the number n here. So it's a numeral for the number n. So what we're going to do is take this language and we're going to add a new constant to it. So this is the language appropriate for the standard model here. So we extend it by constants, in fact, just one constant. Adding a single constant c. And so this constant symbol here has been added, right? So we make the language just a little bit bigger here. So we consider the following sentence. So this is going to be that c does not equal 0 with these n here. And this is what I was calling n. Why don't I just go straight to n here? So it says c is different from n. Right? So we're going to consider the collection of these phi sub n's, these sentences for every n. And we're also going to consider the truths of arithmetic. So what will gamma be? It'll be the collection of these phi n's. And we're also going to throw in the theory of the standard structure. So recall, this is the set of sentences that are true of the natural numbers, the standard natural numbers. So what we'll do is just show that every finite subset of this gamma is satisfiable, it has a model. The compactness theorem will then say the whole lot has a model. But if we think about what the whole lot, what that structure would be, if it was a structure which was true of all of gamma here, all the truths of arithmetic would hold there. But also there would be some new element, interpretation of C, which couldn't stand in for any of the interpretations of the numerals. It would have to be something different from whatever this numeral interprets. So we've added, as it were, a new element. Right? There are things that one can say about C in this new model, right? But things that don't mention C, they're all either in here or their negations are. So there are no new facts about just the arithmetical vocabulary true in this new model. The only new things that we can expressed in this language here are new things about C. So take a finite subset here. Then pick a number sufficiently large that it's bigger than any phi n that's in gamma 0. So that if phi n is in gamma 0, then n is less than k. So now all I have to do is just see that actually gamma 0 is true in the standard structure when I interpret C as K. I take here the ordinary plus times 0 and successor, and I need an interpretation for the constant C. So here I'm going to interpret C here in this structure, n star, and this will be actually the number K. And I'll call this n star. This is being a little bit too informal. Let me just do this more properly here. Here will be the interpretation of C star. Interpretation of C n star is K. And now everything that's there in gamma 0 is true in this structure here. Right? So what's in gamma 0? Some of the truths of arithmetic, finitely many. Well, they're true here, right? Even without mentioning what that is. Then the things that can mention C, there's only finitely many of them. But all the things that are there, they can only say that the interpretation of C is different from n's which are less than k. So that's perfectly true here as well. So the conclusion follows by the compactness theorem. So as here with this n star is a structure in which gamma 0 holds, and gamma 0 is arbitrary, by the compactness theorem, there's an n star which is a model of all of gamma. But now, for this n star, whatever the interpretation of C is, it can't be any of the n's here. But here C star does not equal k for any k. In the natural numbers. So one of the exercises suggests investigating this a little bit more, right? I mean, what this n star would look like is something that looks like the natural numbers with a 0, 1, 2, 3, 4, first element here. And then the interpretation of C is going to have to come after all of these. It's somehow an infinite element that's bigger than all of the things that represent the ordinary natural numbers here. But there's lots more you can say. After all, one of the truths of arithmetic is that every number that's not 0 has an immediate predecessor. Well, that actually means that this C has got an immediate predecessor, because what I just said is true here in n star. So C's got an immediate predecessor. It's also got an immediate successor. But this also has an immediate predecessor. Anything that's non-zero has an immediate predecessor. So actually, there's a whole cluster of these infinite elements. Right? So you're invited to think about that and puzzle out what such an n start could really look like.